initial. Okay, starting the recording. Okay, so today in this course on modern physics, we are going to start the study of the wave-like properties of particles. Okay, so last lecture we studied the nuclear atom, which is the discovery of, through experiment and theories to interpret them, okay, that the atom is constituted by a nucleus, which is very small if compared to the dimensions of the atom, and with the negative charges, which are the electrons, around the nucleus and quite far actually from the nucleus. Okay, so I think we ended with the Bohr atom, which is a very primitive description of the quantum behavior of the matter. Okay, and so it's nuclear. Today we are going to see the wave-like properties of particles. So today essentially we are going to study the Broglie hypothesis. Okay, so we have seen that the light, okay, we have seen the quantization of light before, okay, which was here before the nuclear atom here. Quantization of charge, light, and energy. Particularly, we have seen that light has a particle behavior. So we have seen that light is constituted of packets of energy. They are called photons. They have an energy which is proportional to the frequency. I will call it F. Okay, the frequency of the light through the constant, the Planck constant. And to interpret the Compton phenomenon, it was necessary also to give to these particles linear momentum P, which was equal to the same constant h over lambda. Okay, so photon, particle of light. And now we are going to see the wave-like properties of particles. Okay, so this is very important. I already have insisted on these two equations. The energy of the particle related to the frequency of the wave, okay, through the Planck constant. The linear momentum of the particle related to the wavelength of the light, okay, through the same Planck constant. So the Planck constant relates the particle and the wave properties of light and matter, actually. Okay, so in 1924, Louis de Broglie, he was a student, a PhD student, and he was thinking about these discoveries of the quantization of light, particularly the fact that the light had this dual behavior of a particle sometimes and as a wave sometimes. And I'm not sure, but I think his brother was a physicist. And so he engaged in the study of physics also. And so in 1924, he thought, well, this dual behavior of light as a wave and as particles should be also valid for particle material particles. So we can think of electrons and things like that. So I said, how can I characterize this wave-like behavior of material particles? So this wave will have a frequency which will be the energy of the particle. Okay, so the energy of the particle is something you are very used to, and over the Planck constant, and its wavelength will be the Planck constant over the linear momentum of the particle. Okay, so for a photon, we already have this. Okay, we know that the energy is equal to. We already have these two relations. Okay, E equal of the particle. Okay, the photon we turn it on upside down. Okay, we had a wave and we want to characterize a particle, so we said the energy of the particle is equal to hf, and the momentum of the particle is equal to h over lambda. Okay, so sometimes I will write lambda for particle wavelength. I will write it dB, like decibel, but it is for de Broglie, okay, to call your attention on the fact that it is the de Broglie wavelength of a material particle. Okay, so this was very coherent with the theories existing at the time. The only problem, so the people found it very interesting, but there was no necessity of these relations. There was no phenomenon seeking an explanation, okay, an interpretation through these relations. And so one explanation is that, a thing we can, I think it was de Broglie who saw that you remember when we studied the nuclear atom, okay, the Bohr atom, one of the things Bohr wrote, it was the quantization of the orbital angular momentum. So we had, I will put it black, the orbital angular momentum. Okay, so you remember, we had the postulates were the stable orbits, okay, of the electrons. Here, actually, it's for Bohr, okay. So before the quantization of the orbital angular momentum of the electrons, we had the stable orbits of the electrons. Okay, no electromagnetic emission. Okay, and also we had the emission of light, emission or absorption, obviously, absorption, when electron jumps from one stable orbit to another one. And actually, the quantum number, okay, characterizing these stable orbits and this emission frequency, in this case, you have this emission, okay, of absorption occurs at a frequency f, which is the energy of the higher, okay, I will put it higher orbit minus the lower one, okay, of the two stable orbits, okay, over h, okay. And so this is how you observe light emitted by atoms, although he says that there is no emission during the movement, okay, the movement of the accelerated electrons around the nucleus, okay? And so the third condition was the quantization of orbital angular momentum of the electrons, because you have to, so he wrote MVR, okay? We use a circular, okay, orbit, so we have that the linear momentum P equal to mv, and the position of the electron in relation to the nucleus is they are perpendicular, so the expression of the angular momentum is mvr, okay, and he says this is n, which is an integer, n equal to 1, 2, 3, etc. Okay, n times and h over 2 pi. Okay, and this h over 2 pi, we called it h bar. Okay, because it's very used, okay, in quantum mechanics, and it is also, you know, you have the frequency and you have the angular frequency, which is 2 pi f. Okay, so f equal. So this is very very useful to have some notation. Okay, instead of always writing h over 2 pi, we write it h bar. Okay, so with this new interpretation, okay, of the wavelength, the Broglie wavelength, you have the electron, okay, is a particle, okay, it has an linear momentum, okay, and it has an angular momentum L, M, V, R, okay, around the nucleus, okay. And so when you say that L is equal to an integer number of h bar, okay, what you say actually is that I will try to draw, okay, an orbit. So this is something like that, and I will write, okay, so you have something like, to simplify, I will put 3 wavelengths here, okay? So this is something you know from mechanics, okay, of oscillating ropes. Okay, so if you put a linear ropes, okay, you have something here, you have an elastic rope here, and so you can excite, okay, with a vibration here. So you will have the vibration mode, so you will have the first one, which is like that. So you have the distance, I will call it d, the distance between the, okay, of the box, okay, and so you will have a condition where you will observe the modes, okay, of the rope. So you have d equal here, this is half, okay, the wavelength of the wave, okay, and so you will observe here t equal 2 times half a wavelength, and so on. And so the condition of resonance, okay, of the stationary modes, this is that t is equal to a integer number of half wavelengths, okay. And so instead of having an open box, okay, so what we have is here is a closed one. So you take this extremity and you put it, okay, it's a ring instead of a linear cavity, and so you have your wave, okay, and so it repeats okay? And so here, for example, we will, and when you close the ring, okay, you are exactly at the same amplitude, okay, of the wave as you were, okay, at the beginning. So you close really the wavelength, the wave repeats itself, okay. So here you have the first one and it repeats, you have the 2, 3, so this is some kind of resonance condition equal to this one. And so what is the condition here? This is that 2 pi times, this is, I will call it r, okay, which is the radius of this circle. 2 pi r is equal to, here it's 4, 1, 2, 3, 4, but it's actually n times lambda, okay? Lambda here is complete lambda, complete wavelength, okay? And so you see that you have the same, let me write it. 2 pi, okay? So this is the modes, okay, of the light here, the modes of the, and here this is the Bohr quantization of angular momentum. I'm trying to, so I can write it here, okay? We can write that this is the same thing if we write 2pr, okay, 2 pi r equal to n, same quantum number, h over mv, okay? And so this is, what is h over mv? This is n h over p and h over p, okay, for our electron. This would be, okay, following the de Broglie hypothesis, this would be its wavelength, okay. And lambda, and I will put here de Broglie, okay. And this is exactly, oops, something missing here. Those 2 pi r, obviously. Okay. So this is the quantization of the angular momentum of Bohr, and this is de Broglie, okay? And so you see that it is really, really coherent, okay?
Porque nós temos, Marcos, uma comissão.
Tu peux aller ailleurs, Marcos?
Que está pensando nisso, né? Eu tenho que conversar, deixa eu ver aqui.
Marcos, tu peux aller causer ailleurs? Marcos? Okay, so this is a first sign, okay, that it is really something very interesting and which seems coherent with what we have seen before, okay? So the problem is, how do you put in evidence a wave-like behavior, okay? So you have electrons, you know very well, okay, how to observe the particle behavior of electrons. We have seen it with the Thomson experiment, where he measured the ratio of the mass over the charge of the electron, or the charge over the mass, okay? Millikan, things like that. So electron is something that we can manipulate as a particle, okay? But how do you, when you want to put in evidence a wave-like behavior, what do you do? Well, what you do is you will have some experiment where usually wave light, for example, okay, have a particular behavior, and this is experiments of diffraction and interference, okay? So you never heard before I suppose, okay, as a student, okay, the notion of having diffraction of a particle, okay. So this is interference of particles, okay. So this is what you have to do if you want to put in evidence a wave-like behavior. So what is this? I'm writing here, okay, something about wave interference and diffraction. So remembering here some datas. 1924, de Broglie, as we are looking at it now, okay. He won the Nobel Prize for his discovery because we will see that it is really true, okay. It is accepted now that the particles, material particles, have a wave-like behavior also. So he won the Nobel Prize in 1929, 5 years later. Schrödinger in 1925, he put some more theories on top of this and won the Nobel Prize in 1933. And we are going to see the experiment of Davisson-Germer, and also Thomson, okay? Actually, this is Thomson here. And this is the same year, 1927, okay? These are two experiments where they show that really this dual behavior is also true for particles, okay? So both Davisson and Thomson won the Nobel Prize in 1937. I don't know why Germer didn't win the Nobel Prize together with them, okay? So let's have some revision about the wave interference and diffraction. And so here, diffraction is what? You have here an aperture, okay? And you can also observe diffraction if you have some object, okay? Okay, some object which should have a very sharp edge, okay? So for example, they always show a razor blade, okay, you know, I won't design it, I don't know how to design this, but it's a very sharp edge, and if you look very carefully, you will see a series of fringes, okay, so maybe it would be better to put here some image, okay, I will put some image of diffraction, okay, by an aperture or by an obstacle, okay? And so what you see, for example, here is when you have some aperture of width A here, you won't have this kind of behavior, okay? So this would be a geometrical ray description. So a part of the light here, incident, will be stopped by the screen here, and the only part that will pass, okay, through the aperture, will have this shape on the screen, okay, an observation screen here, and this would reproduce exactly the shape of the aperture, okay. So you can observe that, okay, but in certain conditions you don't. And what you observe actually is that you observe a diffraction pattern, okay. So you have really this big shape in the middle, but on each side of this expected bright region, okay. This is bright, obviously, okay. This is where light reaches the screen. You have other parts, okay, away from this central part, okay. And so this is diffraction. And actually, you probably have studied it in physics, okay, in basic physics. So one-slit diffraction, this is what I show you here, okay. And so you have this kind of central shape, okay, and symmetrically, okay, you have other less and less bright, okay, fringes, okay. So the intensity profile is this one, okay? So you have a wide central region, and you have other less brighter, okay, regions away from and symmetrically from the central part. When you have here a two-slit interference, so this is something different. So here it depends on the aperture, okay, of the slit. And here we have two-slit interference, okay, so you have one slit separated from another one, and the distance between these two slits, okay, is d, okay. And what you observe, okay, this d here, you observe a pattern of fringes, okay, which are regularly separated here on the screen. And actually, if you take it into account the diffraction by each slit, or meaning that here you have an aperture width A, and here also, you will observe this kind of patterns. And so you have a zoom on the central part, okay? This is this one, okay? But inside it, now you have these fringes, okay? So you see the fringes, and so the intensity profile, okay? So it's only a revision. The fact is that these patterns, they are related to the wave-like behavior, okay, of light, because you have interferences. And so you can show that these, for example, these bright fringes here in the two-slit interference, they are where you have constructive interference between constructive interference. And here, the dark ones, you have destructive interference, okay? And so to have interference, you have to have waves, okay? And it is important to emphasize here that you have significant intensity diffracted at angles which are, here I called it theta, okay? And so the order of magnitude of this theta is such that you have typically a sine theta equal to a number m, a quantum number, okay, it's not a quantum number, it's an integer, okay, times lambda. So the order of magnitude of this theta would d sine of theta equal m lambda, okay? And so the order of magnitude of this angle, you can relate it to the ratio between the wavelength and the aperture of the dimensions of your, okay, your object, which is can be an aperture or an obstacle, okay? And so let's have some calculation of the order of magnitude of this angle, okay? So if you, I think an angle of 1 degree, okay, you can think you can observe it, okay? So this is something very macroscopic. So you have visible light. So visible light, I will say that it has a wavelength of 500 nanometers. Okay, this is green. And so this is the center, okay, of the visible light typically. And so I will use this value for lambda. I will use 1 degree for theta, and I will calculate, okay, the dimension of the aperture, for example, so as to observe this kind of phenomenon, okay, in this 1 degree, okay. So you calculate it, and you find that the aperture should be of the order of 30 micrometers, okay. So this is something you can do, okay, physically, particularly now. 100 nanometers is 1/10 of a millimeter. So these are things that we can think of doing physically, okay. So you can observe diffraction of visible light, okay, with physical aperture, okay. And you can put a lens of diameter 1 centimeter, okay. So this is very small. And when you use mirrors, lenses, okay, thin lenses, okay, so in an optical setup, for example. So you have dimensions which are of this order of magnitude, 2 centimeters, okay? And so what is, for the same wavelength, what is the angle, okay, where you will be able to observe diffraction, okay? So this will be 0.003 degrees. So this is very, very small. So what I want to emphasize here is that in order to observe, okay, effects of diffraction, okay, essentially you have to have aperture of the dimensions of your object which are similar, okay, to the wavelength, because what will, okay, you know that sine of theta is between 0 and 1 typically, okay, so it gives you to have something visible, okay, so you have to have an aperture, okay, comparable to the wavelength. So here this is much larger than the wavelength, okay. Here you have 5 × 10⁻⁷ meters. Here you have 1 × 10⁻². So this A is much larger than the wavelength, and so you won't observe any diffraction effect, okay. So knowing that, we are going now to calculate why don't you observe, okay. Okay, de Broglie said the particles, they have a de Broglie wavelength, okay. So in basic physics you studied the movement of particles, okay. For example, you said that a horse was a particle, you said that a ball was a particle, okay. So it was a point, okay, with a mass, with a velocity, okay. And so what do you need to observe the wavelength behavior, the wave-like behavior of a ball, okay. So let's calculate this. So what is the de Broglie wavelength of a ball, okay, of mass 1 kilogram and velocity 10 meters per second, okay. So this is something you can do, a ball, 1 kilogram, this is very big, but here actually you see I won't calculate exactly, I only want to have the order of magnitude of this de Broglie wavelength. So you have the mass, you have the velocity, so you calculate the linear moment, m, mass time speed, okay, and so you will have 10 kilogram meter per second, okay. And so the de Broglie wavelength will be h over p. So you have h, which is 10⁻34, okay, and you have p, which is 10⁻⁴, okay. And if you orders of magnitude, we essentially compare the powers of 10, okay. So you will have 10 to the power, okay, 10 to -34 -1, 10 to the -35 meters, okay. So you can say, well, why not? So let's compare it with the typical dimensions of an atom, okay, okay. The Bohr radius, okay, for example, which gives you the typical size of an atom, is 0.5 something angstrom, okay. So 0.05 nanometer, okay. So this is 10 to the minus 10 to the minus 10, 10 to the minus 11 meters, okay? And here you have 10 to the minus 35, okay? What are the typical dimensions of an atom nucleus, okay? Remember when we studied Rutherford, okay? We saw that we could have an idea of the typical dimension of an atom nucleus through the calculation of the smaller distance an helium, okay, an atom actually could charge, okay, could be close of a nucleus, okay, in a collision, and we found that this was of the order of 10 to the minus 15 meters, okay, and so it's still 20 orders of magnitudes larger, okay, that's this one. So obviously you won't observe the wave-like behavior of a ball of mass 1 kilogram and velocity 10, or whatever the velocity, okay? So what do you have to do? You want to do what? This is very small. You would like to have a larger de Broglie wavelength, okay, to observe it. So the mass of the ball, you are not going to be able to decrease it. So you will have to take a smaller particle, a lighter particle, okay, so smaller mass, smaller speed, okay. So let's see here. To increase the possibility of observing the wave-like behavior, okay, of a material particle, okay, this may have a larger wavelength, the Broglie wavelength, and therefore a smaller linear momentum, okay. So let's calculate, okay, the de Broglie wavelength of an electron, okay, which is something we can manipulate, of kinetic energy 100 electron volts, okay. So we don't give here the velocity, we give the kinetic energy. This is not that high kinetic energy, actually, okay. You how do you obtain this kind of kinetic energy for an electron? It is already in electron volts, so you only accelerate an electron by voltage of 100 volts, okay. So this is really not difficult, and you have this kind of energy very easily in your laboratory, okay. And so this is you have the mass of the electron, which is of the order of 10 to the minus 31, so it's almost 10 to the minus 30 kilograms, okay. So you have the expression of the kinetic energy. I was saying this was not very big because you have to be careful when you calculate the kinetic energy as a function of the velocity. This is the classical expression. This is not relativistic, okay? So you can accelerate electrons to velocities such that you have to calculate their energy through the sometimes obviously not here, through the relativistic equations, okay. So this is a classical expression of the kinetic energy, and so we can write it, or also we will use a lot of this expression, okay. The kinetic energy is p squared over 2m, okay. So you can calculate the linear momentum, okay, which is the square root of 2nk. You put the numbers, okay, and this is 100 electron volts, 100 electron volts. Each electron volt is 1.6 10 to the minus 19, okay, joule, okay. And so the answer is P is this guy, 5.4 10 to the minus 24, okay, kilogram per meter per second. And so you calculate the wavelength, the wavelength of this electron, and you find something of the order of 10 to the minus 10 meters. This is angstrom. This is something you can think, okay, this is comparable. This is, if it were, it is not light, okay, this is not electromagnetic radiation. This is a material particle, okay, and so this is the de Broglie wavelength of this particle, but it is similar, okay, the wavelength is similar to the wavelength of X-ray, which are electromagnetic waves, okay? Electromagnetic wave, okay? This is not an electromagnetic wave, okay? This is a material wave. So you remember we can do diffraction with X-rays, so probably you can do diffraction with electrons. And actually you can use, as the wavelength is very similar, you can use the same kind of apparatus, okay, to diffract electrons, okay? So as I say here, this is still very small, okay? This wavelength is very small, but is at the same order of magnitudes of the dimensions, the size of the atom or the interatomic spacing in a crystal, okay? When we saw the diffraction of X-ray, do you remember? I will remember it here. This was diffraction of X-ray by a crystal, okay? A metallic crystal. And this was, we saw it when we were going to study the Compton effect, and the Compton effect uses this kind of electromagnetic waves. Okay, they are very energetic. Okay, the wavelength is very small, the energy is very, very high, and so you have to have a crystal, okay, to diffract them. So this is the apparatus of Davisson and Germer. Okay, they did this experiment. So this is, you have a filament here, so you heat or you pass a current, okay, through this filament, so you will have emission of electrons, okay, this is this thing, this is an electron, and so you have, okay, this is between these two, you accelerate, okay, this is a heated filament, and this is the voltage to accelerate this electron, and so here you control, okay, you control the kinetic energy of these electrons. And so, if it's true, okay, you control, if de Broglie hypothesis is true, you control their de Broglie wavelength, okay? And so, a beam of these electrons is incident of a crystal. This is the same nickel crystal we already used, I think, for the diffraction of X-rays. And so, you put a detector, okay? And this is very easy to detect electrons, okay? This is a charged particle, so this is, so you put this detector at an angle which is called phi here, and what do you expect? Okay, so if it is really, it can be described as a wave, okay? I remember here, you have two planes, okay? You have here, this is a crystal, nickel crystal here. And so inside this crystal, you have families of atomic planes, okay? And they are separated by the interspacing D, okay? It is called D. And you can characterize, okay, any crystals. If you know the wavelength of an X-ray you use, okay, you can, through X-ray crystallography, you can characterize your crystal, and so you know the value of this interspacing, okay? And so here we have an example of this diffraction. So you have here your beam of X-rays, okay? Or, as we are doing here, electrons, okay? And so there will be incident, okay, at an angle for Bragg diffraction. What we call theta is this angle between the incidence direction and the plane, okay, of diffraction, here, theta. And you can see here that we call phi. Phi is this one, would be this one. This would be this one, okay, phi. Incident detected, okay? So you have, what is the condition? The Bragg condition, remember? They will interfere, okay? These two rays here, this one was reflected by one plane of the family, and this one by the following plane of the same family. And so here, up until here, they are in phase, in phase, in phase, in phase. This one will be moving, okay, distance d sine theta 2 times, okay, and so here there will be, okay, at the same phase difference, okay, And so depending on this phase difference here, you will have, okay, destructive or constructive interference. Okay, so the Bragg condition for constructive interference, obviously, is that this path difference between the two rays, okay, is 2 times d sine theta, okay. It is an integer number of wavelength, okay, m equal 1, 2, 3, etc. Okay, and so the relationship between phi, okay, of the Davisson-Germer experiment and this condition theta here, you have theta, which is pi over, okay, theta is here, and here you have phi over 2, okay. So 90 degrees minus phi over 2. And so the result of this Davisson-Germer experiment, okay, for a kinetic energy of the electrons of 54 electron volts, okay, they observed, okay, a very strong diffraction, okay, diffraction peak, okay, at this angle phi equal to 50 degrees. So this is something, this is a polar, okay, representation, okay. So you have the, for example, how do you to draw this kind of, this is real directly related to the experiment. You see, phi, so phi equal to 0. This is in the direction of the incident beam, okay? So you don't observe nothing. And so when you look at this angle, for example, I don't know what angle this is, okay? But this is something like, I don't know, if this is 50, this is 20, for example, 20, okay, 20 degrees. So what is the intensity, okay, the number of electrons detected as a current, probably, okay? So you put it in the length of this, okay, of this line, and this is lesser, okay? You see, if you increase the angle from this one, you will have less intensity, will be smaller, and here it will be smaller. And what you see is for this one, 50 degrees, okay, you have a strong maximum, okay, polar coordinates. Okay, so what does it mean? It means you are apparently observing diffraction, okay, and so they observe for 54 electron volts electrons, okay, a strong diffraction at phi equal to 50 degrees, okay. So it means if 50 is phi is 50 degrees, theta is 65, because 65 plus half, okay, phi over 2, which is 25, 65 plus 25, you will have 90 degrees, okay, pi over 2. So theta is equal to 65 degrees. From X-ray measurements of the, okay, okay, crystallography, it is known that D, okay, is equal to 0.091 nanometers. So you calculate here the wavelength, okay. Sorry, you apply here the Bragg condition, okay. So you have a strong maximum, okay, at this angle. So this angle is 65 degrees. D is known, okay. And so what is the wavelength corresponding to this one, okay? If it were X-ray, what would be the wavelength of the X-ray? So this is twice, okay, this D, this is D, okay, sine 65 degrees. And the answer is that the wavelength would be, okay, if it were an X-ray, it would be 1.65 angstrom. Okay? Well, it was not X-ray, okay? So we will calculate through the prediction, okay, using the de Broglie wavelength, okay? So you calculate the linear momentum, twice the mass, okay, times the kinetic energy, you take the square root, okay, blah, 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 you calculate, and you obtain almost 4, okay, 10 to the minus 24 kilogram meter. You divide the Planck constant, okay, by this linear momentum, and you obtain 1.67, okay, angstrom. So, seems very nice, okay? So, obviously, these are really, okay, you have the errors of the experiment. So I put some numbers here, 65, blah, 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 but it indicates really that it seems that it is really true, okay, that these material particles which have a mass, which have a particle-like behavior, okay, very well known, okay, they also have a wave-like behavior, okay. So at the same time, same year, J.P. Thomson, which was the son of J.J. Thomson. Remember J.J. Thomson? J.J. Thomson was the guy who discovered the electron as a particle. Okay. And his son discovered that the electron is a wave. Okay. So, J.P. Thomson won the Nobel Prize in where is it? I wrote it. Here, okay. He won the Nobel Prize in 1937 with Davisson, okay, for the discovery, for the experimental demonstration of the de Broglie hypothesis, okay. So what was the experiment rapidly of J.P. Thomson, okay, J.P. Thomson. So he used actually he used a larger electronic energies, okay. So I wrote it down to 40, a fraction, okay, a fraction of kilo electron volts to a few tenths of a fraction of, okay. 10 to the, I will put here fraction of kilo electron volts, okay, to 40 kilo electron volts, okay. Marcus?
Yes.
Sorry. And so he didn't use a crystal, okay. Here you have a solid crystal of nickel, okay. So he used a film, okay. So the film is as if you had a powder, okay. And so in this film, you didn't have a very good crystal, okay, with long range crystalline structure. Actually, it was more small pieces of, okay, you have some places, okay, this is a crystal, very beautiful one, and here you have another one, okay. So you have crystalline structure, but at short range, okay. It's not at long range as in a Davisson-Germer experiment. And so what you observed, what is the advantage of this kind of experiment? It is that you have all the angles, okay, of diffraction, because in the film you will have all the orientations of the planes, okay, the family of planes. And so for one direction, okay, here you have the incident beam, okay, on the film, okay, and so you will have a few, it is as if it were X-ray diffraction, okay, And so, for example, here, for this film, you have the X-ray, okay, diffraction. This is a wavelength 0.071 nanometers, okay. And so they use the same apparatus, okay, but instead of using X-rays, they used electrons. And so for electrons with a kinetic energy of 600 electron volts, for example, corresponding, if you calculate their de Broglie wavelength, okay, it would be 0.05 nanometers, slightly smaller than this one, okay? And so the angles will be smaller, and you have to increase a little, okay, to compare really the diffraction patterns, okay? But you can see, okay, that this is X-ray, this is electronic diffraction, okay? So these are two very beautiful experiments, okay, showing that de Broglie was right, okay? So you can observe, okay, the wavelength behavior of material particles. So particularly, since then, okay, it has been almost 100 years, okay, the wave-like behavior of particles has been observed, has been manipulated, has been used, okay. We have now a branch of physics which is called matter wave. You have the matter waves, okay, matter waves. These are this kind of waves. When you have a de Broglie wavelength, it is not electromagnetic waves, okay. And you have optics, okay, matter optics, where you manipulate, okay, not electromagnetic wave, but matter waves, okay. And what the obvious application of the electrons, okay, as waves, okay, is the electronic microscope, okay. So what is the advantage of the electronic microscope if compared to the X-ray microscope? Okay, so imagine you can imagine that X-ray is very dangerous. It is a very energetic particles, okay, and so an X-ray microscope would have a very good resolution, but it's very complicated to have an X-ray microscope. Electrons are much okay. You see here 600 electron volts, so this is no big deal. You can have this, and with this kind of energy, you have this kind of wavelength, and you can image. Okay, you can look through things. Okay, with the same resolution with an X-ray, but with in better conditions. Okay, it's much less dangerous. Okay, so I will stop here this presentation because I don't have time today to actually we have finished. Okay, this is an introductory part to the wavelength particle, the wave-like behavior of matter, okay. And so we have a few aspects still to study before entering the realm of the quantum physics, okay. And this will be next class will be still on this this subject, and probably with some problems we will solve, okay. And after that we will study, well, electromagnetic waves. How do you study the propagation of electromagnetic waves? You have the Maxwell equations, okay? So you deduce from the Maxwell equations a wave equation, okay? And so you will describe everything you want for an electromagnetic wave using the Maxwell equations. What is the equation describing the behavior, the propagation, the behavior of a matter wave? And so this will be the Schrödinger equation, and we will see it this is the last topic of this course. And so we will study it, okay, and through essential aspect, okay, some insight it gives into the quantum mechanics, okay, and so and how you can make measurements, okay, in quantum mechanics. So I will stop here.